So in this video, we'll be going over the disk method, and the formula that you need to memorize is volume is equal to the integration from, let's say, limit a to limit b of pi r is a function, and I will be explaining this right now, squared dx. Now, you might be asking, why is this radius in terms of a function? So let's say we have a cylinder here where the diameter or the radius is fixed. So at every point it's the same, right? The radius. Now, what if we have another cylinder whose diameter or radius is changing at each point? So let's have a look at this radius. You can notice that in the middle the radius is less, and as it goes up or down the radius is increasing. So that is why we have r here as a function. And actually, when we have a curve and we are rotating normally against the x-axis or the y-axis or against any line, we will have a reflection, and this is what a cylinder would look like. So I will do a lot of examples, so don't worry about that. So that's a basic overview of what this is. Now let's quickly go over the washer method, and then we'll do some examples. So the washer method is quite similar, except that we have normally two um, cylinders, and we have the outer cylinder, which is the largest cylinder with capital R radius, and the smaller inner circle or cylinder with the radius of lowercase r, as you can see in this. And the area that we need to find is the shaded area over here, this graph. And the formula is integration of pi r squared is the same, except that we are minusing and we are finding the shaded area only. And again, we can integrate against dy or dx. It depends on where we are rotating. So now let's start with some examples, and this will be clear. So here we have a line x is equal, no sorry, x plus 2y is equal to 2, and we are rotating or revolving about the x-axis. So what do we do? The first thing that you always need to do is graph it. Since you will, if you have a visual image of the graph or the volume, it is more easy to find it, and that is always the first step. So let's graph it first and take, also we notice that this equation is not in terms of x, like y is equal to ax plus b. So we also need to rearrange that, and we are rotating about the x-axis, so we need it in terms of x. So here I am going to rearrange it. So 2y is equal to 2 minus x. I just brought x to the other side here, and now we divide the entire thing by 2. So y is equal to 1 minus x over 2, and this is what we are graphing. So now let's just take any random points for x and y, 0, 1, 2, -1, and graph it. So here, when y is 1, x is 0, and when x is 0, or sorry, when y is 0, x is 2. So these are the two intersections, and let's draw the graph now. So 1 and 2, and it will be a straight line. So let's do that. I'm gonna raise the point. So here is what the graph looks like, and one thing I forgot to mention is that the volume is bounded by the y-axis also. So now we need to rotate this, or we need to reflect this on the x-axis, since we are rotating about the x-axis. So let me draw a reflection line over here, same as this one, and this will be in a different color so you guys can see the difference. So here is the reflection line, is just a reflection on the x-axis. So if it's saying that you're rotating about the y-axis, then you draw the reflection on the y-axis. So here the area that we're looking for is bounded by the y-axis, which is the straight line, vertical line, the x-axis. So this is the area, right? So now if I draw a disk inside, let me make it bigger. The outer disk will be from here, a disk inside would look like this, and so on. So you'll have infinite number of disks inside this, tiny, and remember that this is a 3D model. So I'm drawing it 2D right now. It's going to be very thin layers of disk inside. And remember that we are starting from the y-axis, so it will be, the limits will be the intersections. So let me change my color. It's going to be the integration from 0 to 2, since the intersection on the y-axis is 0 and the intersection on the x-axis here, this point, is 2. So 0 to 2. And here, what is our radius? If you look at the, if you try to find the radius over here, it is, I'm gonna erase this right now, the disk, or I'll change my color to blue. The radius of this disk is simply right here, right? It's always going to that line, and for the small one, it's also going to the line. Oops, that's not going there. So how many disks that we have, every radius is going on the line, right? Which line is equal to this part over here. So we can say that our radius here is simply the line of cohesion in terms of x here. So it's going to be pi, I'm going to take pi outside, and then r squared here is going to be 1 minus x over 2 squared dx, and that's simply it. So here now we just simplify this. So it's going to be pi, and I'm going to open the square, so it's going to be a squared minus 2ab, which is 2x, or sorry, it's going to be x. So x over 2 times 2 is x, plus b squared, which is x squared over 4 dx. And now we integrate this, so it's going to be x minus x2 over 2 plus x3 over 12, and everything is multiplied by pi. And now we put the limits 0, 2, and now we simply just substitute 2 in x and then minus it by 0, and 0 is going to be entirely 0. So if we substitute 2 here, we'll get 2 minus 2 squared over 2, which is going to cancel out, plus 2 over to the power of 3 over 12 multiplied by pi, and the final answer you'll get is 8 over 12 pi as your answer. Let's do an example where we are rotating against the y-axis this time. So moving on, we have the line of equation, which is x is equal to 3y over 2, and we are rotating about the y-axis, and we are also bounded by y is equal to 0. So again, let's graph this out. And remember, when we are rotating against the y-axis, we need the equation in terms of y, since it's going to be rotating like this. So that's there. Now let me draw the line, which is equal to a straight line here, and it is also bounded by y is equal to 2. So we have a horizontal line over here, which is y is equal to 2. So here now let's draw the reflection, which is going to go something like this, and our disk inside is going to look like this. So this is one disk, this is the second disk, and so on. But our boundaries are from y is equal to 0, which is this x-axis basically, and y is equal to 2. So our last disk here would be something like this. What do you think the radius of this disk would be? It's from the what is this line, y-axis, all the way to the line, right, which is the line of equation. So once again, our radius is going to be x is equal to 3y over 2. So let me show you that again. It is from this point to here, right, and then this point to here, touching on the line always. So radius of x here is equal to 3y over 2. And remember, when we are rotating against the y-axis, your equation also needs to be in terms of y, which we already do. So here we can just plug in the formula by integration from, now that the limits are very important here also. So we are bounded by y is equal to 0 and y is equal to 2. So this line over here is 2 and this line is 0, and we are integrating or finding all this area over here. So the limits here is going to be 0 to 2, and then r squared here is going to be 3y over 2 squared and dy this time, and then you simplify this and integrate this. So here it's going to become integration 0 to 9y squared over 4, and then 9y3 over 12, which is 3 over 4y squared multiplied by pi, and we substitute 2 and 0, 0 is going to be 0, so it's basically 3 multiplied by 2 to the power of 3 over 4 pi, and the final answer would be equal to 6 pi. And the integration is not the main focus of this topic. The main focus is how do you visualize it and find the volume, and are you integrating the proper limits, the proper radius, and so on. So you shouldn't have any issue with the integration. The main issue or the main problem question here is finding the graph and then finding the radius of the disk inside and so on. Now let's move on to where we have trigonometric functions. So in our next example, we have the equation of x is equal to tan pi over 4y, and we are rotating about the y-axis, so this is very important, and we are bounded by y is equal to 0 and y is equal to 1. So let's draw it out now quickly. Now you should know how a tan graph looks like, but if you don't, you can substitute any random values of y here and you'll get x value. So the graph here would look something like this, and notice that we are bounded by y is equal to 1 also. So we know our limits of integration is going to be from 0 to 1 of the equation. Since we want to find, I'll highlight the area here, this area basically. So simply, if you want to see the reflection, it is going to look something like this. Okay, let me do that again. That's even worse. Here my reflection is not accurate, but you can notice that this is the area in shaded in red here, and if you want to draw some disk inside, they will look something like this. So this is one disk, this is the second disk, and so on, and we have infinite number of disks inside, and another disk right here. Oops, that's not working out, and you get the idea. So it's the same idea again and again. Now we want to find the radius of each disk here, so it's going to be from the y-axis all the way here, touching the graph again, right, and so on, here, 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 here. So our radius here is going to be equal to the line of equation, which is in terms of y, and that's what we want since we are rotating against the y-axis, tan pi over 4y, and just apply the formula. So now what is our limits going to be? We are starting from 0 and we are stopping, we are bounded by y is equal to 1 here, right? So our limits is going to be 0 to 1 of r squared, which is tan, r is basically tan pi over 4 y. So here I'm going to do tan pi over 4 y squared dy. And here you do need to use substitution to get rid of the angle over here, pi over 4, and then use secant squared minus 1 to replace tan. So I'll do that quickly over here. So u here is going to be equal to pi over 4y, and du here is going to be equal to, again, pi over 4, since pi is a constant, and dy. So now you can replace this part by u, and we will be left over with, and since we need to substitute dy is equal to du multiplied by 4 over pi, and we realize that this pi will cancel out with our outer pi, so all we will have left is 4 outside, and then integration of 0 to 1 tan of u squared. And now we can replace tan u squared or tan u squared with 4 integration and then secant squared u minus 1 du, and the integration of secant squared is tan u, so 4 into limits for 0 1 tan u minus u, and remember to substitute u back to what it is, so u is pi over 4y, and then you find the limit, so you get the idea here. So let's move on to our next example. And actually the final answer you should get over here, if you want to recheck your answer, is 4 minus pi. Let's do one more example of disk method and then we'll move on to washer. So here we have y is equal to sine x cosine x, and we are rotating about the x-axis, and we are bounded by x is equal to pi over 2 and x is equal to 0. So the graph looks something like this. This is half, this is pi over 2. So again, the same steps here. We know that the radius is this curve, which is equal to y, which is equal to sine x cosine x. So here all we need to do is integration from 0 to pi over 2 of r squared, and r squared is the curve again, since it's always going and touching that. So I'm going to take pi outside, sine x cosine x squared dx. And here we do need to use the half angle identity, which is equal to sine 2x is equal to 2 sine x cosine x, and here we have sine x and cosine x, so I'm going to bring 2 over there. It's going to be sine 2x divided by 2 is equal to sine x cosine x. So we need to replace this now with this part over here, 2 over 2, and here when we square this, it's going to become sine squared 2x over 4, and I'm going to take 4 outside, and it's going to be pi over 4. I'm going to do 1 over 4 times pi, so pi over 4, and now we can remove this, and once again we need to use our double angle now. Since we cannot integrate this, we need to change it to our identity, which is equal to sine squared x is equal to cosine 2x plus 1 over 2, and here we have 2x, so that 2x is going to become 4x. Also remember that we are multiplying the angle by 2, so here this part is going to be equal to cosine 4x plus 1 over 2, and now we integrate this normally. You can integrate cosine and 1 over 2. So one small mistake that I made here is that the half angle identity is 1 minus cosine 2x, so here it will be 1 minus cosine 4x. Sorry about that. So this is the half angle identity, and cosine squared x is equal to 1 plus cosine 2x over 2. And the final answer that you should get over here is equal to pi squared over 16. So now let's move on to the washer method, where we have two lines or curves equations. So y is equal to 4 minus x squared, y is equal to 2 minus x, and we are rotating about the x-axis. So now the first step is to graph this, and this is a parabola, and we have a minus sign in front of that x squared, so it's going to look like an n, and we are 4 units above. So let me draw that out here. And now the straight line also has the y-intercept as 2, and then the x-intercept as 2, or sorry, the x-intercept as 2 also. So we do have an intersection over here. It looks something like this. And also, to find the intersection, we can just equate both of the equations. So 4 minus x squared is equal to 2 minus x, and here we will have minus x squared plus x plus 2 is equal to 0. And what two numbers multiply to 2 and add up to 1 over here? And remember that we have a minus sign over here, so we need to flip whatever we have. So we are going to get x plus 1 into x minus 2. So here the two intersections are x is equal to minus 1 and x is equal to 2. So now let's draw the reflection and see what we are solving for here. So here we know that we are bounded by these intersections, which are -1 here. So our first disk here would be right over here. And again, my drawing is not the most accurate, but bear with it. And we have infinite number of disks inside. So let me draw one disk from the parabola inside, and the smaller disk inside would be the disk which is bounded by the straight line, right? Like over here. So these are the two disks that we have, and this is why it's called the washer method. If you have a look at the washer nut, it has a hole inside. So now, what is the radius of the outer bigger disk? It's from this point, let me draw it out, and it's in red by the way, till the x-axis, right? And if we have another disk right over here, it will look something like this, and so on. So the radius of the outer disk over here is always bounded by the line which is equal to 4 minus x squared. So our Rx is equal to 4 minus, okay, let me make more space over here, is equal to 4 minus x squared. And now let me change the color, and let's look for the smaller disk radius, which is this disk right now here. And let's say if we have a disk right here, it will be always bounded by that straight line, right? You see that? So here our smaller disk is equal to 2 minus x. And now let's plug in the formula. So once again, if you drew the diagram, it is very clear that you can distinguish between what is the outer radius and what is the inner radius, like here. So if you draw a disk inside, let's say over here, and we have the inner disk which is equal to, let me remove, okay, I cannot remove that. So there will be, let me make this bigger. So here the inner disk would be from here till that line, and it is always bounded by the straight line, and the outer disk is always bounded by the parabola. So here the smaller disk radius would be this part, and the larger disk radius is always from here to here, which is both are bounded by the parabola, and the smaller disk is bounded by the straight line. So that is why we chose this here. And now let's just plug in the formula. It will be pi. The limits is always the intersections, which we found over here. So -1 and 2, and we can even visualize over here. So this is the first intersection, and this is the second intersection. So -1 to 2, and then the outer radius squared, so 4 minus x squared minus 2 minus x squared dx, and you integrate this normally. And integration is not a problem here. It's very simple. We just expand everything and we simplify it, and then we integrate it. So that shouldn't be an issue. But the main thing here is understanding what we are doing in the graph. So that's it for this video. If you have any questions, let me know in the comment section, please. And let me know the answer if you want to recheck your answer in the comment section. And thanks for watching. Also, I forgot to mention that I did make separate video for each of the methods, the disk method and the washer method. If you want to see more examples, you can check those videos out. And thanks for watching.